Welcome to our second day, which of course can't equal the first day and so has to be completely different. What we're doing today, a very natural thing, is to try to show how computing research has actually blossomed since those heady early days. What we could do, of course, is to try to cover the whole of computer science worldwide, and that would be ridiculous. So we're remaining unashamedly parochial and talking about our own work. I hope you'll forgive us for that. Please take it as read that we understand that many wonderful things happen around the world. We want to convince you that many wonderful things have been happening in Cambridge over the last 50 years. We had thought of doing it, as it were, by decades, but it doesn't work out like that. What we have is a steady progression leading from then up to now, more or less. One of the things that I tried to do when I took over as head of department was to try to understand the research in the lab, and I found it best to understand it as traditionally a large tranche of engineering work, always building new systems, and that seems to form the core of our research. But what gets added to that is two other what I call great themes, which of course is a worldwide phenomenon. That is the theme of the human-computer interface, which includes everything from natural language processing, artificial intelligence, graphics, all of those things, everything to do with the human interface on one side. Think of that above the engineering, and then below the engineering, the development of the formal mathematical understanding of computing, where ideas trickle down from practice into some kind of theory. So, of course, what has really happened in the engineering is that it's become more network engineering, more communication engineering as every decade goes by. That's, in fact, one of the themes we're going to take up right at the beginning with our first speaker, who is Professor Andy Hopper. He was appointed to the lab in 1979 after doing his PhD here. He's always been involved with making communications work, allied to computing. He's recently been appointed to the engineering department, but we like to think of him as still at heart a member of us as well as them. And he's someone who, with his Olivetti Oracle Research Laboratory, now AT&T Research Laboratory, has combined industrial and academic research with skill and balance for the last, I don't know, decade and a half, 2 decades probably. He's going to talk on rings and things, the Cambridge ring, etc. So over to Andy Hopper.
Thank you very much, Robin. This is the first time ever I've given a historical talk, so you'll have to bear with me. I might not be quite as polished as some of my illustrious colleagues. So my time slot in the computer lab is from 1974, when I came as a PhD student by accident. Of there being a EPSRC studentship cancellation at the last minute here and me knocking at the door at the appropriate moment in time, until about a year ago when I went down the road. I fished out 1 or 2 photos just to give a little timeline. So here is, oops, wrong way around. Here I am. Bjarne Strustrup is in the audience. We shared a room for many years. Bruce Croft, who is now at UMass. Jeremy Dion, who is at Compaq, previously DEC. Mark Pizarro is Canadian, working in Canada. And Carl Dello, who's made a pile of money being an entrepreneur in the Valley. So that times when we were obviously at that stage, very influenced, very proud to be part of the line of work that started with Morris. And so there is the thing. So I'll talk about rings and things. By things, I mean things attached to the rings. The Cambridge ring started after Morris went to another visit. He's got a very good nose, right? So he went off, sniffed at a company called Hasler in Switzerland. And he saw a simple ring system, a modest ring system, which was used for transmitting voice, speech, telephony type of application. And he came back and essentially said, we will work in this sort of direction. And that was a time when there was no higher speed communications. The cables and so on that were in use were at a few K, maybe a few tens of K for the wider area systems. And so we set about designing this system. As in many things, David Wheeler was pivotal to all this, and we designed a 10 megabit ring network consisting of repeaters, which were the things that received, retransmitted the signal and so on, to which were attached what we called stations, to which were attached, which was the network logic, to which were attached access boxes, which bridged between the device and the station. And power went round the ring as well. These are my old slides, so some of you may also nostalgically think of the HP plotter that made this actual slide, which is itself, you know, one of those that is 20 years old. Anyway, it was quite quick, 10 megabits. The error rate ended up being quite low. Used twisted pair. Repeaters were powered from the ring, so even if all this went up in smoke, it carried on, and the maximum distance was about 100 meters between repeaters. So this was Project C. And so we got going and built this system, and it really started being deployed in about 1976 in use, and it was an inherently small packet system. It had 2 bytes only that you transported between different places. So that's the root of the whole multimedia line that has subsequently followed, and the world as a whole hasn't really quite got there yet. It's only just beginning to converge between using synchronous and asynchronous type traffic in a broad sense. So here is a picture of a repeater, which consisted of the power supply section. There was 48 volts that went round through a transformer and powered this bit. Here are, you know, David put up these core diagrams. Well, here is still use of cores. In 1974, 75, 76, this is to extract the power to get your 48 volts out, because it was AC, but here they reappear. That little diagram he showed is relevant here. A little bit of logic, a phase lock loop, and so on. Here is the back side of it, wire wrapped, and the connector which went to the other station logic. And here is, forgive me, I'll put up some very busy ones, but just the idea of this one is this is the complete ring repeater logic, circuit diagram, everything. So this is primarily, I think this was Norman Unwin's handwriting and drawing, and I well remember him. I was just on the periphery of this. I was a, you know, short trousers research student just trying to help out a little bit, and my memory of Norman is anytime I approached him, his response to me would be, "What do you want? You want shooting, don't you?" And this was absolutely consistent. But then, of course, as was said yesterday, he was brilliant and gave me the answer that I was striving for. In particular, around here is the phase lock loop, which generated the clock. And I still don't understand how that works. Maybe, David, you do. Norman Unwin had it. Anyway, if you look at the voltages, normally you have a voltage-controlled oscillator, and you put in a voltage, and you move it up and down, and it chases the frequency. Well, this thing's got an AC signal like this on it. I don't think anybody understands. It's all magic, really. It continues to be magic to this day. We used twisted pair. Another little thing I remember, there were pairs of twisted pair, and David came up with a modulation scheme, which is in a curious sort of way a code division system across both wires. And on longer sections, we didn't know why this didn't work very well. And we scratched our heads and messed about until we discovered that we were using pretty poor twisted pairs, and the lengths of the 2 twisted pairs were different after a certain stage because they were twisted at different rates, both deliberately and crudely. And so the signals, there was group delay in broad sense, but the signals traveled a different physical distance, in effect, down the 2 pairs of wires and got out of sync and so on. So eureka, the solution was beyond a certain length to cut it in half, cross over the wires, and everything was happiness after that. This is the station logic. So it just shows you, this was in part driven, what can you do reasonably in a lab? And TI LS74 theorist logic was the bee's knees. We all had that orange book we looked up things in. We could construct a reasonably complex thing. Here is the backside of it. You notice the colored wires, exactly the same on previous designs. There was, pin 3 to pin 7 between any pair is color such and so on, and it was maintained. This was hand wire wrapped, we didn't run out of color wire wrap stuff. And again, I put on a very busy one, but here it is. This is the complete. This is David Wheeler's handwriting logic. The complete Cambridge ring station ring logic, and it's also a totally flat design. There was no further hierarchy here. That's it. David is a man who, for many years, has done things on little bits of paper, right? And there were, 7 or 8 bits of paper, and I learned from this, for better or for worse, and I think mostly for better. Most of my designs are flat like this. You just hold it up there. But it also means that it can be optimized and rather more function can be extracted from this. The most bizarre thing I can think about this is, I don't know if any people remember that date, is the bizarre coding that put the station number onto the physical plug that existed on the board that had this. It was bizarre. And of course, once you had many stations, each one had to have a different arrangement of this wire, which shorted 5 volt and 0 volts. And we sometimes had to be rather gracious when remembering David's design from that point of view. Now, Morris's entrepreneurial spirit, and the world was a different place. That design of the repeater and that design of the station logic was handed out to visiting companies. And so as to avoid the bureaucracy of the university, insofar as it exists, they were told, here it is, it's yours, just give us some money, and you better make it 3K. And so Morris collected handsomely, I believe, on this, because many companies came by, and the Cambridge ring came into play. Steve Wilbur at University College did the PC board layout, so here is a repeater PC board layout, and here is a station logic layout, but it's exactly the same sort of thing. My recollection of that time is of the very large number of visitors who came to see the Cambridge ring. It really started working about 1976, and me, I happened to be the one at the time who was doing the tours. I must have done the tour, I don't know, 250 times. I mean, it was just amazing. But I enjoyed it. It was good exposure for me, and my colleagues were good enough to look after me in every way. This is moving on to chips. So there are really 4 themes I want to talk about in this brief lecture. One is the theme of how communications technologies themselves were developed here and promulgated. Secondly, how VLSI, the use of VLSI, CAD and the VLSI chips themselves were promulgated as a result of some work here. Distributed systems themselves, and then finally multimedia systems. So I started with communications technologies. I'll come back to that because that was the ring and its promulgation to many places. But it was at around that time, and really this was the back end of my PhD and then becoming a research assistant before I became an assistant lecturer in 1979, was the design of chips for implementation of this. So this is a picture of the Cambridge ring, the 10 megabit thing, VLSI design based on Ferranti gate arrays, ULAs, uncommitted logic arrays as they were called. I bumped into a fellow called Thomas at the Rutherford lab in about 1977. I said, this is good, we could do that. And he said, here is the money. So I turned up at Morris's door. I said, I've got some money. He says, you better become a research assistant quick, and I'll be the principal investigator because you can't be unless you're a staff member. So that's how all this started. Rutherford paid for it. Subsequently, a government project called the Advanced Computer Technology Project, ACTP, paid for it, and Ferranti were the chosen manufacturer. Now, the world hasn't changed to this day. We had terrible trouble with this design because the CAD wasn't there. These were 1,000 gates per chip uncommitted logic arrays, so you had to cram everything in 1,000 gates. They were actually uncommitted transistor arrays. So we could put the analog bits on there. And I made the stupendously dumb mistake of actually changing the slot format, the packet format, put in an extra couple of bits, so inherently made this incompatible with the previous rings. The reason for that was because we felt we were ahead of the game and would have this out working before too many of the old style, the PC board versions, would be out there. The other problem, as with all chips as far as I can tell, the design speed was 10 megs and it only ever worked at 7. This has continued, and in all design seems to be like that. I well remember, there was no CAD for this. I'll just say a word about CAD in a sec, but I well remember getting these chips back and them not working, and we used to probe them, right? We used to probe them. So one of the purchases I remember having signed off is for a slab of marble from the monumental mason down by the cemetery, which I went to purchase to give me a heavy thing on which I could do the probing, and going to biochemistry next door and getting little micromanipulators, which you then had a wire, you put it in acid, put a current, got a little thing, and we were peering at it and poking away, and half the time damaging the track and making it go bad. Anyway, the end result of this is that the BBC machine had these sort of things inside them, because we learned on this, we built up a whole CAD infrastructure, specification, layout, back annotation, all this sort of stuff. Peter Roberts and Jeremy Dion were principally involved in that. That was observed by me, and I was involved with Acorn, and the reason the BBC machine had such good graphics and such good serial interfaces, because Ferranti ULAs were used to essentially design to paint a triangle faster on that machine than on any other machine, and I think that was one of the principal reasons that machine did well. There were many other reasons, but that was a principal one. So the introduction of VLSI, or this sort of thing, to Acorn and so on, came from this, and then subsequently the whole CAD line to do with the ARM, and now the company ARM draws itself right back to this start in the computer lab right here. So that's chips. Let's get back onto Cambridge rings. I said repeater, station, and now the access box. So this is back to communications technologies just for a minute. Again, this is the design of what became the most ubiquitous Z80-based both access box and endpoint in particular. So here are the control signals that went to the ring, back and forth from the ring. Here is some memory. Here is the Z80. Here is the oscillator. Martin, I don't know if you're here, but Martin Johnson, 14th of December, 79. That's his drawing. And it's really here that we started to learn not just about the ring, the associated station logic, repeater logic, but what's an interface. Today they're called deep interfaces, shallow interfaces, interrupt this, DMA that. How much protocol do you put in the machine itself? How much protocol do you put in an intermediate thing? How much protocol do you put in the actual design? What can get in your way? How much does back pressure help you when you transmit and you get a busy back? What does that mean? There was a Wheeler fitment which stopped you even knowing what happened under certain circumstances, which was another one of these things where people had to be very sympathetic to the design. We really got going on that at that sort of stage. And most of these, or many of these, were built 68001, 68502, 6809, all that sort of stuff. So that communications technology went from there. And then a very large distributed system was built. Again, these are my old slides. Roger and Andy Herbert, many others, I noticed some are here, where we put together a distributed system based on this ring. And so we went from a stage, so now we're talking distributed systems, we went from a stage where you had a terminal attached to a time-shared system, and you got some cut of that, to a situation where you had terminals attached to networks, services of various kinds attached to networks, a processor bank with a bunch of processors, and you went to a resource manager, said, this is my requirement. The resource manager went to something, worked out what's available, and delivered to you that what you wanted, and principally it wasn't time-shared, it was your own, but you then gave it up when you finished. So wonderful, wonderful work which expanded our understanding of distributed systems, and most aspects of what is in use today can be found in here. So be that, say, the laser printer, the image was assembled on another machine which had the specification of what should be done, should be printed coming from yet elsewhere, and this was before postscript. And this also included very, very simple, what is today called thin interfaces, ones that almost have nothing attached to them. The pointing machine for wire wrapping was the simplest one of those. This basically was a motor which went zip, zip, and then you could do the wire wrap at that position. And that just had a single register to which you could put the next position. And the whole computation for what should be happening and so on was done elsewhere in this distributed system. And there were some bizarre things like, an Algol 68 resource manager running on a Z80 controlling all this. So, that's to do it. But we learned. So this was, the ring caused this wonderful set of distributed systems, and it lasted until about 1976. You won't be able to see these, but I've got the drawings of how the ring was essentially around the time it was shut down. There were 3 rings, and when you add up the number of stations and so on, the number comes to about 100. So there were 3 rings. An interconnection of rings became a hot issue, a project called Project Universe, followed by a project called Unison, were substantial projects which not only linked clusters of rings on a single site, but rings between different sites using satellite in the first case and then ISDN in the later case. Sorry about the quality. This is the Titan room around that sort of stage. This is Ron van der Hoorn. There was a big collaboration with Acorn at that stage. He was paid for by Acorn. He was an Acorn employee. That's the processor bank. The 68,000s were done by him and came from Acorn, or at least were paid for by Acorn. So the processor bank, all those machines are up there. He's fixing it. Here is Neil doing something or other. I'm in the middle of this picture, but I've taken myself out because you wouldn't want to have a fright. Dan Kraft, Brian Knight, who's somewhere out here, is right there. And I can't identify this person, but there it is. Many, many good people. We were always ahead of the curve in terms of technology with Ring versus Ethernet, fast Ring, FDDI. We never quite made it big. We made it big with Ring in the UK, but we were driven with this VLSI thing and high-speed networks. So we carried on and designed what's called a fast ring, which was designed to work at 100 megs. It only worked at 70 by definition, right? And the important thing, I remember designing this primarily with Roger in the office up there on the chair. And the point here is that we went to multiple rings and these things called bridges, which enabled you to bridge one ring onto another ring. Today, that would be called a switch, because what it's doing is taking several packets, mini packets, which are coming around this way, 32 bytes by now, and deciding where they should go. In other words, the bridge can receive on many addresses, or what today are called VCIs. Okay? And the back pressure doesn't work the same. It's difficult. You've got this funny thing in the way. So previously you got some response saying it got there, it didn't, and it was a directly available thing, modulo David Wheeler's little thing. Here, you had fog in the way. So that's really one of the key properties of ATM, and in the early 80s when the implementation of this started, we were thinking about those lines. This became an ECL repeater, big problems having that made, a CMOS network controller. The company went bust, another one came along. But anyway, the CAD, the VLSI line, so this is a fast ring station chip, the CMOS network controller, packet buffers, custom standard cell, some PLA type structures and so on. And again, the whole CAD system that supported this came with it. I well remember, it's one of these moments where I get a bit tipsy, with John Porter being at a company called Mytech in Belgium when the first test program actually tested all this, and it worked after maybe 3 years of work. Didn't publish a single thing, just worked on this 3 years, non-stop. And it worked, and it really did work, because by the time the test program runs, it really does mean that. So we were very happy, and that was all essentially paid for in the bulk by Acorn. And then David Greaves carried on and designed a gigabit ring, which worked essentially at 700 megs. Light modules, fiber, lasers, Plessey, ECL chips used in tandem, VME bus, and off we went. So to finish off, I'd like to just bring you a little further up to date, because all that network infrastructure enabled us at all times and I think it continues today for fixed and radio systems, to attach a variety of things. And I think the most complex thing that was attached, and that was in the late 80s and early 90s. Again, it was a system, Pandora, which was done jointly with Olivetti, what is now AT&T. And we built a whole bunch of these, 40 or so, and it was a workstation, which was actually an Acorn workstation, a separate box with a ring, but still an ATM. We run it in ATM mode, and then cameras and all sorts of things attached. A complete subsystem which handled the data part, not the signaling part, the data part of multiple streams in a very rich way, where we could try many different applications. And the system, my last slide, the system, again, this is an old slide of mine, got really quite substantial and quite complex. So this shows the computer lab side, this shows the Olivetti, jointly funded by Digital at that stage, side. There were many Pandora's boxes. You see there are rings running at 50 megs. We slowed it down, 500 meg, the fast ring, backbone ring, bridging between those, bridging between Ethernets and those, the Pandora's boxes themselves, then all sorts of workstations, repositories, real-time communication in the one direction, real-time communication in both directions, all kinds of applications, things like video phones were tried, video mail, latest news, you could look into somebody else's office. This was reciprocal, so there was a whole protocol. This thing popped up and you went like that, and then you had to go away because it was impolite after about 2 seconds, I guess. And this was a wonderful experimental system, which I think taught us about the fourth component of what I've been talking about, and those are multimedia systems. And really, I haven't seen any evidence in the wider area of something that is in use of this kind to this day. So the 4 areas, I'll show you some video clips, but the 4 areas I covered were basic communications technologies, starting with the ring and the variety of higher speed rings and the interfaces that go with them, in particular for handling video and audio as well as other kind of traffic. The VLSI line, which both has helped ultimately our friends at ARM be such a wonderful success that they are today, but also, for example, in digital now, compact, Jeremy carrying on there. Distributed systems, which were in the early 80s, this country was way ahead in terms of understanding. Many universities had such systems. And finally, of late, this was deployed in 1990, multimedia systems, again, based on high-speed networks. Now, the other thing that's happened with multimedia, it's gone digital, and so it never goes away. And so, while it was hard finding the material for some of the older stuff from about 1990, nothing got thrown away. So we've gone to the backup tapes and found some of these Pandora things. And so let me just show you these. We had this thing which
hello there, this is Andy Hopper.
Which was called Chaps, where everybody just introduced themselves. We started small, and then we went big.
Hi, I'm Peter Robinson.
Now, the video side was deliberately not accentuated, because remember, this is a fully network distributed multimedia system with multiple streams and so on. And we deliberately, this was, I well remember talking about this at great detail, kept this side.
Hello, I'm Neil Weissman.
I'll play that one again. It's good.
Hello, I'm Neil Weissman.
Nuance. Multimedia's nuance.
Hi, I'm Ian Wilson.
And even though the video is grotty, these people come to life.
Hi, this is Frank Kelly.
Kent.
Hello, I'm Brian Brown.
Wonderful relationship. Dec paid for quite a bit of this.
Good morning, this is Don Galvez on one of my aperiodic but frequent visits to Cambridge University, ORL.
Frank Folside from engineering.
Frank Folside here, making an occasional visit from engineering, about 100 yards across the road to the Apple.
But of course, not everything was perfect.
Hello there, I'm Mike Adelphi. Hello there, I'm Mike Adelphi. Hello there, I'm Mike Adelphi.
Hello there, I'm Mike Adelson. Hello there, I'm Mike Adelson. Come on, one of these has got to be good.
Doug Shepherd from Lancaster.
Well, this is Doug Shepherd, sitting in the Automotive Research Lab. I must say I'm very impressed by this depository. The idea of being able to send images of myself to every member of my staff is really very appealing. I hope we soon have a system like this running at Lancashire.
Okay, so that was from a network server supplying video streams. I'm not quite sure how many could do at once, but several, and one-way stuff. The other thing we used was video mail, and you know, we were optimistic. So here is somebody sending me video mail. Allegedly, he says it works.
Just a quick message I need to say, everything seems to be working now. All we need is the more memory for this machine and a new motor for the autofocus.
He forgot to put a light on in his room, and he's... A visitor to the lab was Bob Metcalf in the early 90s.
Andy, hi, this is Bob Metcalf, of course. Got your call about Bill Strecker. Strecker never called me. If he's still considering Cambridge, and if you gave me his phone number, I'd give him a call and encourage him. Please let me know. I'd love to talk to Bill anyway. I know him from years ago at DEC. This is Metcalf, over.
It was very interesting having him here then, because we could reflect upon our sort of sparring. He won, but upon our sparring in the late 70s. And David Greaves.
Hello? It started. Andy, this is a message from me to you. I've got a letter here from Christoph. Well, it's from Christoph's Institute in Poland. And it says, Dear Dr. Greaves, we are very grateful that you have accepted our invitation to attend the 1991 specialist seminar with a paper entitled Cambridge Backbone Network, an overview and preliminary performance results, co-authored by Kay Zielinski. So, I don't remember submitting.
You get...
Andy, in Re, I just had a XP confer call from Roger, and it didn't tell me who it was. It described him as a question mark, which I think you will agree falls rather short of any proper description of
Okay,
Roger.
3 more, but they're quite good.
Hi, I have an inquiry from Microsoft about badges, and I've forgotten the name of that chappie who visited us from Microsoft, Hungarian name, I think. He visited us a few weeks ago. Can you recall his name, please?
So that's me to Roger, early 90s.
That chap from Microsoft, I shall have to dig back in the diaries. I'll let you know when I've had a look. It was actually more than a few weeks ago. It was December, wasn't it? Wasn't it Dr. Myhrvold, M-Y-H-R-V-O-L-D? I've got a record of such a chap listening about the right.
Okay, thank you very much.
Thank you very much, Andy. That was priceless. I'm sure there are a lot of questions you'd like to ask, but we're going to move on. We have a lot of different things for you. Each one's different this morning. Right at the other end of the spectrum, more or less, Mike Gordon's our next speaker. He was appointed in the lab in 1980. Mike and I had been close colleagues in Edinburgh, where we'd begun to work on the question of formal verification of this, that, and the other. And Mike very sensibly came to Cambridge and began to score a succession of breakthroughs in machine-assisted reasoning. I believe he's going to tell us about verifying verifying a computer with the help of another computer this morning. I'd like to say that, of course, his work moves on into verifying software as well, and it's a fulfillment of a program which has probably taken 2.5 decades up to now, something of that kind. Mike Gordon.
Thank you. Well, as Robin said, I joined the lab. I think I was hired in 1980, but I didn't turn up until 81, which was just the time that Maurice Wilkes was leaving. And in fact, the first letters I had in connection with my appointment were from Maurice. And then later on, I started getting letters from Roger Needham. In fact, what happened was I was working in the States, and I applied for the job having seen an advertisement in the communications of the ACM. And a bit later, I got a rejection. Sorry, don't get the job. And then to my delight, somewhat later, I got an email message from Roger saying, we seem to have got another post. Are you interested? So I went up for an interview at Xerox PARC, where Roger was at that time visiting, and eventually I got offered the job, and here I am. I'm going to talk about primarily work done in the 80s on proving computers correct. So what that means is you take a computer and you produce some sort of mathematical description of it, and you analyze that to show that in all circumstances it works. That's the dream, of course. So instead of just testing it on a few test vectors, you try and establish by some kind of theoretical argument that the design is completely sound. So that was the dream. And in the 80s, here at Cambridge, we looked in detail at two computers. They were both extremely simple. One was Tamarack, and this was a completely toy machine invented entirely for doing experiments, theoretical experiments, writing papers, and so on. And in fact, I originally designed this when I was at Edinburgh, just leaving Edinburgh, working with Robin. I did some sort of paper analysis and then came to Cambridge and started working here. And about this time, Graham Birtwistle, who was at the University of Calgary then, sent me on a visit an extremely bright student, Jeff Joyce. And he needed a little project, so I suggested to him that he use the theorem prover we had just built to have a look at this toy machine. And he learned the theorem prover and did the proof in I think 4 weeks. It was an amazing achievement. And then he went back to Calgary, and later he got an internship at Xerox PARC, and on the side he built this machine. And in fact, I have the chip he made. Not sure what happens if I put it here. And was never really used, of course. I think he tested it, and it seemed to step through a few cycles okay. And then Jeff Joyce came to Cambridge, and he did a very good PhD here. And I'll tell you a bit more about him later. And this little toy machine actually became a standard example. Now, in the theoretical world, we often have standard examples for areas. So if you're interested in recursive functions and analyzing them, you might use the factorial function. If you're interested in showing that imperative programs do their thing, you might use a sorting program, quicksort. And this little computer has sort of become the standard little toy computer that people use to first try out their ideas if they're trying to verify a computer. So it lives on. It was never a real machine, but it has a kind of continued existence. And indeed, I heard just the other day that someone was doing a project on systems on a chip design, and they were going to use a version of this just as sort of proof of concept. So that was one machine that we looked at. And the other machine was, in some sense, a more realistic machine. This is the Viper. And the story there was that people at the Ministry of Defense in the Royal Signals and Radar establishment had heard about the work on Tamarack that Jeff Joyce and others had been doing. And at the same time, they had been building this computer, Viper, which was intended to go in highly critical applications and to be extremely reliable. And they intended to use formal methods to try and increase its reliability. So when they heard about stuff going on here, they got in touch, and eventually they placed a contract with us to have a look at the verification of this machine. And we did. Tamarack was a micro-programmed machine microprogramming, of course, being invented by Maurice Wilks, and Viper was hardwired. So that was one difference. And as I said, RSRE gave us a research contract to verify parts of Viper, and we did some, I think, quite exciting work on that. Initially, it was done by Avra Cohn, who's my wife, and later it's continued by Wei Wong, who's now in Hong Kong. And this raised many issues. The Viper machine is not that much more complicated than Tamarack as an architecture, but it was a kind of real product. It had, glossy flyers. This is the Marconi implementation glossy flyer. And attempts were made to sell it. But there was an unfortunate, some would say unfortunate, saga associated with this. During the research, what happened was that the RSRE handed over the design of Viper to a company called Charter Technologies, gave them a license, and Charter Technologies started marketing Viper. And as marketing goes, you make extremely strong claims about how wonderful your product is. And this made us a bit nervous at Cambridge because there are a number of other groups in the States, for example, also doing computer verification. And we knew that the claims that were being made about Viper weren't really entirely accurate, and that these people in the States would notice this and cause a fuss. So here's an example. Let me read it. I dug this out of some brochure. It's not too extreme. Viper is the first commercially available microprocessor with both a formal specification and a proof that the chip conforms to it. Well, when we saw this sort of stuff, Dr. Cohn wrote a paper to protect ourselves against these sort of claims. And in fact, she was lucky in that she was invited to submit a paper to a fairly high-profile Journal of Automated Reasoning. And she wrote a paper which made a number of obvious points and used these to discuss the general issue of what it means to apply mathematical techniques to an artifact like a piece of silicon, like this. And she made a number of obvious points, like a physical chip, here's a physical chip, isn't actually something that a mathematical proof applies to. A mathematical proof applies to a model of the architecture of a chip like this, not actually to the piece of silicon. But this kind of thing was somewhat blurred in the marketing hype associated with this product. Also, we had only looked at a rather abstract view, so-called register transfer level view of the architecture. We hadn't looked at sort of thing David Wheeler is an expert in, detailed electrical design. And we'd only analyzed this Viper under certain limited circumstances. For example, that no interrupts occurred. And even with all those things, we'd only done part of it. Well, so Avra Cohn wrote a paper describing what we'd done, and it's actually was a very influential paper. It was republished in a big collection of papers and is still cited. But the people, Charter Technologies, who were marketing Viper, were very unhappy. In fact, they sued the MOD and they sent us threatening letters saying that we were publishing stuff which was damaging their business. And, controversy ensued. It's unclear what the upshot of this controversy was. I mean, was it overall good or bad? In some ways it was bad because it led to a suggestion that there was overselling of formal methods. Locally, for us, it was quite good because it gave us very high profile and we got lots more research contracts to continue doing this sort of thing. Well, that's the Viper saga. I'd like to say a little bit about how one actually goes about proving a computer correct. So what you do is you have to describe what the computer is supposed to do, and you have to describe the implementation which achieves that or is intended to achieve that, and to show that the second achieves the first. So you write an interpreter. This is a technique we used in the 80s and indeed is still used for the execution of machine instructions using a functional programming style. And that's the description of what it's supposed to do. And then we represented the actual design by a gigantic logical formula. And then we used a theorem prover to show that the gigantic logical formula, in fact, had the behavior described by the interpreter. So here's the sort of guts of what's involved. From the programmer's point of view, you have a memory and some registers. And in these simple sorts of machines, Tamarack and Viper and so on, you execute a single instruction and you get to a new state. The register's changed and the memory changes. Now, the way this is implemented is there's some more complicated set of devices, including some extra registers which are just used for control. In the case of Tamarack, there's the microprogram store and various microprogram registers. And in order to perform a single step as seen by the programmer, the hardware actually takes a number of steps, 6 or 7 in the case of Tamarack, micro steps. So what you have to do is to show that if you compose together the several steps of the implementation, you get something equivalent to a single step of the machine. Well, in order to do this, one needs to represent everything in some kind of notation that one can reason about. And we used notation called higher order logic. And this was developed initially in Cambridge by Bertrand Russell, Trinity College. He developed something called the ramified theory of types. And then later on in the 40s in America, Alonzo Church developed the theory of simple types. And that's what higher order logic is. I was reflecting when I was thinking about what I was going to say in this talk about the following fact. We were talking in a staff meeting the other day about how, on the face of it, the computer lab is being ripped off because we get lots of research money and the university doesn't give us all that we earn. In fact, they use the research money to subsidize other disciplines, say the humanities. And we were wondering whether, we were grumbling about this a bit. But in fact, here I am in the 80s using stuff which was developed by the humanities. So in fact, this is a good thing. It should. This is a slide which I actually yanked out of my lecture notes for the course I'm going to give next term on hardware verification. And it's just to give you an indication of how you take something that looks like a computer architecture, there it is, just a bunch of things connected together, and generate a formula. And you can sort of see, without me explaining what's going on, that you plonk things down corresponding to the components, and then these lines, which are the internal lines, you localize using this thing called an existential quantifier. So anyway, there's this method of taking a schematic diagram and generating a gigantic formula, and this method came from a number of people, Professor Hoare, Keith Hanna at Kent, and a postdoc, Ben Moskowski. They were all influential in evolving this technique. So, you've got this gigantic formula, and you've got your functional program describing what a single step is, and you want to prove that a single step is correctly implemented. And what you do is you symbolically execute both the abstract machine that is the specification and the implementation. So what you do is you have some variables which correspond to the contents of the various registers in memory, and then you sort of calculate a large, very large formula which gives the values of the registers in a successor state in terms of the values in the current state. And you do that both for the programmer's view and for the hardware view. You get two expressions, E1 and E2, say, and then you try and prove that if you jettison the stuff in the implementation which can't be seen by the programmer, that's what I've called by this operator abstract, that the result of that is equal to the change of state from the specification. And that's normally a huge case analysis plus some algebraic simplification. the case of Viper, the case analyses were typically 1,000 cases or so. But it's not quite that simple, because a single step of the machine, from a programmer's point of view, might actually be allowed an unbounded number of steps in the implementation. This, of course, depends on the architecture. But in the case of Tamarack, for example, no assumptions were made about how fast the memory would respond. What happened in Tamarack was, if you wanted to look up a value in the memory, you just had a very simple handshake. You would say to the memory, I want the contents of the following address, and you'd put it on a bus, and then you just wait. And sometime in the future, the memory, and there were no assumptions were made about how fast it was, would say, okay, I've got your result, and then it would give it to you. So there could be some unknown number of cycles that the processor was waiting for the memory to respond. And there was here's a familiar sort of diagram showing a handshake. So the question is, how do we deal with that? It's not as simple as just executing a fixed number of steps at the abstract level and a larger number of steps at the implementation level. But fortunately, the humanities came to our help, or in general, have come to the help of lots of computer science. This is a picture of A.N. Pryor, who's a philosopher. He's a New Zealander who went to Manchester and then went to Oxford, and he invented temporal logic. And temporal logic was invented by him, I suppose, about late 1950s. And it was imported into computer science by a number of people, in particular my PhD supervisor at Edinburgh, Rod Burstall, Amir Pnueli, an Israeli who won the Turing Award for doing this, and a number of other people. But in the context of analyzing memory protocols, the work was done by a chap called Bockman, who I believe was at UCLA. And this work was taken by Jeff Joyce as part of his PhD and used. Now let me just give a hint of what a sort of thing Pryor came up with. What we want to require of the memory is something like this. If there's a request on some line to the memory, D-request, then it must eventually be acknowledged. So if it's never acknowledged, of course, the machine will just stop. It'll ask to look up contents of an address, and if the memory is crashed or something, it'll never happen. So in order to prove that the computer is working, you have to have an assumption like this. And this is how it's written in temporal logic. So humanities to the rescue. The form of an Oxford philosopher. Now, temporal logic is one example of a notation. And during the 80s, we did a lot of work on other special purpose notations, trying to deal with them in a uniform way. And we did this by embedding them all in higher order logic, this logical notation developed by Russell. So if you like, one can see this as a technological confirmation of the philosophical doctrine of logicism. Logicism is this idea that every kind of truth can be reduced to logical truth. Russell and Whitehead tried to show that this was the case by defining numbers and so on in terms of logical notions and then deriving the laws of mathematics. What was done here is we took notions from temporal logic, which were introduced as separate notions, and then via a semantic analysis of them, reduced them to just the kind of logical notions we have in higher order logic. So this general idea is not due to us at Cambridge. What we did was we used this idea for a technological purpose. So that's proving computers correct. Let me mention a number of other projects that went on at the computer lab during the 80s. You saw the ECL chip. It was on one of Andy Hopper's slides. Andy Hopper had a PhD student, John Herbert, who did some very interesting work on verifying this. Don Gaubatz, who I haven't spotted, but I see he's on the... Oh, hi, Don. He designed a complete ring sort of toy ring, a bit like Tamarack is to computers, the Gobat's T-ring is to networks, and that was verified by another PhD student, Tom Mellon, who's now a professor at Glasgow. And finally, moving now into the 90s, part of the switch of the Fair Isle network designed by Ian Leslie was analyzed by Paul Curzon. So that's some other work. Well, what about modern microprocessors? I've talked about stuff in the 80s. I can't resist saying a little bit about the future. And the problem is they're just horrendously complicated. It's currently only feasible to verify small fragments of current microprocessors like Pentium-class machines. Not only are they enormously complicated, so the tools we have are not up to the scale, but it's very complicated to even understand what it is they're doing, because they typically execute instructions, lots of instructions in parallel and out of order. So there's a lot of activity trying to just deal with this complexity. But there's also a recognition that correctness is absolutely critical and that existing tools are beginning to have a really hard time. So all the major processor manufacturers have so-called formal methods groups, mainly doing kind of research-oriented stuff rather than actually dead in the middle of the design team, and there are many exciting projects going on at the moment. But it's a very tough area, and it's hard to keep up. So here are some people who did PhDs at Cambridge and are now doing formal methods around the world. There's Jeff Joyce I mentioned. Most recent one is John Harrison, who's gone off to Intel to do things he won't tell me about. So the side effect, one of the side effects of this work on the 80s is that we built theorem-proving tools in order to do these tremendously complicated proofs. And in fact, two tools have come out of the computer lab, the Hull system and the Isabelle system. Isabelle was not primarily used for hardware verification, so I haven't talked about it, but it's a system developed by my colleague Larry Paulson, which is very widely used. It's a beautiful general-purpose theorem-proving system. And Cambridge is unique, I think, in having two world-class theorem-proving systems distributed from it. There's about 6 such systems in the world, and we have, a third of them. So we're doing very well in this area. So I've pretty much finished now. But if you're interested in some more popular history, there's a new book coming out by Donald Mackenzie, who's a professor of sociology at Edinburgh University, called Machines and Dreams of Reason, Computing, Risk, and the Sociology of Proof. And he has a chapter or two looking at the kind of things I've been talking about. Thank you.
Well, thank you very much, Mike. So we've seen two contrasting pieces or lines of research, engineering, applied theory.